Hello friends, welcome to our channel Knowledge Amplifier. So today in this particular video, I am going to discuss one very interesting and very important concept related to matrix, which is surely going to help you in understanding many algorithms in machine learning and data science topic, and that is diagonalization. So this particular topic also you might have studied while studying application of differential and difference equation course in your engineering. Just a quick recap I want to give about diagonalization. Okay, so for understanding diagonalization, you should have a clear idea about eigenvalues and eigenvectors, which I have already discussed in my previous video. So if you want to know that, please go through the link given in the description box. And without any further delay, let's start our today's discussion, that is diagonalization. So what is that? Suppose we are having a square matrix. So I am discussing with 2 cross 2 matrix. Same concept you can map for any n cross n square matrix. Okay. So this particular matrix we have to convert to diagonal matrix format. Diagonal matrix means only diagonal elements will be having some values, rest all elements will be 0. Okay, that's what the problem statement is. Okay, now consider for this matrix A, the elements are A, B in the first column and in the second column C, D. And for this matrix, we are having two eigenvectors x1 and x2, where x1 and x2 both will be having obviously dimension as 2 cross 1, because this transformation matrix is 2 cross 2, so the eigenvectors will be 2 cross 1, right? So transformation matrix is n cross n, that time eigenvectors will be n cross 1. That's what I have already discussed in detail in my previous video. And these x1, x2 are eigenvectors, and lambda 1 and lambda 2 are corresponding eigenvalues. So that means what? That if you just do A multiplied by x1, that is, if you want to apply this transformation matrix A on this vector x1 and x2, then in the outcome vector, that will be also another vector, right? So for that, the direction will be same like this x1 and x2, only change will be in terms of magnitude, and that scale factor is basically lambda 1 and lambda 2, right? That's what the eigenvalues concept. So in simple words, we can say ax1 equal to lambda 1 x1 and ax2 equal to lambda 2 x2. Okay, now let's compute the value for this particular case. So ax1, what is A? ACBD. What is x1? PQ, one column vector. Do multiplication. So what will be the result? So 2 cross 2 multiplied by here 2 cross 1. So output will be 2 cross 1 matrix, 2 rows, 1 column, right? So if you multiply A multiplied by P, so AP plus CQ, so that is the first element. Second element will be BP plus DQ, right? So this is what we are getting for AX1. And what will be the value for lambda 1 x1? Lambda multiplied by PQ, so lambda 1P, lambda 1Q, that's it. Okay, so this particular 2 cross 1, this vector and this vector are same because ax1 equal to lambda 1 x1. So we can say first element of this particular 2 cross 1 vector is nothing but first element of this particular vector, right? So we can say AP plus CQ equal to lambda 1P. That's what is written here, right? Similarly, BP plus DQ equal to lambda 1Q. So these two equations we have got from this particular one, where ax1 equal to lambda 1 x1 is known. Similarly, if you consider the second equation, ax2 equal to lambda 2 x2, if you just substitute, what we will be getting the value for ax2? That is A, B, C, D and Rs, because x2, this particular x2 vector we have considered as Rs, right? So if you compute this particular multiplication, you will be getting AR plus CS, and second element will be BR plus DS. Okay, what will be? So sorry, here this actually will be lambda 2, ax2 equal to lambda 2 x2, because for x2 the corresponding eigenvalue is lambda 2, not lambda. Okay, so lambda 2 x2 will be lambda 2 multiplied by x2, which is Rs. You will be getting this value. So this particular vector and this vector is same, that is first element will be equal to this element and second element will be equal to this element. So AR plus CS equal to lambda 2R, BR plus DS equal to lambda 2S. Okay, so these two equations and these two equations we are getting from the equation ax1 equal to lambda 1 x1 and ax2 equal to lambda 2 x2. Simple, right? Nothing rocket science I did till now, right? Now suppose we want to compute this particular one. So what is this? A, which is our transformation matrix, multiplied by first eigenvector we are taking in the first column, second eigenvector we are taking in the second column. Because if you see that this matrix multiplication is justifiable, right? Because this is 2 cross 2 and x1 x2, if you create a matrix like this format, it will be also having 2 cross 2. So x1 is nothing but pq, one column vector. x2 is also nothing but rs, so the column vector. So those two column vectors are now becoming column of this matrix. So this is what we want to compute, suppose, and let's see what result we are getting. So if you multiply 2 cross 2 matrix with 2 cross 2, outcome will also be 2 cross 2, right? So A multiplied by P plus C multiplied by Q will be first element. A multiplied by R plus C multiplied by S will be the second element. B multiplied by P plus D multiplied by Q will be the third element. And B multiplied by R plus D multiplied by S will be the fourth element. So simply we are getting this particular 2 cross 2 matrix after doing this particular multiplication, right? Till now, very simple. Now just substitute these values, whatever we have got in our previous equation. So if you see AP plus CQ, see here, AP plus CQ equal to lambda 1 P. So I have substituted lambda 1 P here. AR plus CS, if you see AR plus CS equal to lambda 2 R. So I substituted by lambda 2 R. BP plus DQ, what is the value? See, BP plus DQ is lambda 1 Q. So I substituted here lambda 1 Q. And BR plus DS, if you see BR plus DS equal to lambda 2S, so substitute lambda 2S. So what we are getting, that A multiplied by x1 x2 when we are doing, so if you see this particular one, don't consider these first two lines, just ignore these first two lines. If you come to directly this line, A multiplied by x1 x2, that is our transformation matrix multiplied by a matrix. And how we created this matrix, considering the first eigenvector as first column, second eigenvector as second column. For this we are getting result as lambda 1p, lambda 2r, lambda 1q, lambda 2s. This is nothing but the same what we are getting here. Okay, right. So we can just readjust this particular right hand side matrix and we can write like this way. So if you see, I just decomposed this particular 2 cross 2 matrix as two different 2 cross 2 matrix. So A multiplied by x1 x2 equal to PRQS multiplied by lambda 1 0 0 lambda 2. So if you multiply these two matrices, you will be getting back this particular matrix. So nothing wrong, right? P multiplied by lambda 1 plus R multiplied by 0. You will be getting first element. Like that you can check. Okay. So what is this particular matrix? PQRS. That is nothing but, if you see, PQRS is nothing but this x1 x2, this particular matrix only. So I am replacing here that one. So this is equal to x1 as first column, x2 as second column, like that, whatever matrix we are getting, multiplied by this particular one. So this is nothing but a diagonal matrix where first element is first eigenvalue, second element is second eigenvalue, and this first eigenvalue and this particular first eigenvector are related. So corresponding to this eigenvalue lambda 1, the eigenvector is PQ. Corresponding to this eigenvalue lambda 2, the eigenvector is lambda RS, right? That's what I have shown here. For lambda 1, the eigenvector is PQ. For lambda 2, eigenvector is RS, right? Okay. So we are getting this particular one. So this particular matrix, what is the current situation? A multiplied by x1 x2 equal to x1 x2 multiplied by this kind of diagonal matrix, where in diagonals we have basically our eigen values. Okay, so this particular matrix we can give this particular symbol, and this x1 x2, that is the matrix what we are getting by putting the eigenvectors as column, let us consider as S. That time we can write the same equation as AS equal to S lambda, this bigger lambda. Okay, this is very important equation. So what this equation is, A is our transformation matrix, S is nothing but a matrix which we formed with first column as first eigenvector, second column as second eigenvector, and so on. And this particular one is what? There is nothing but a diagonal matrix which is having the eigenvalues along the diagonal. Okay, that is first eigenvalue is nothing but corresponding to first eigenvector or first column of this S matrix. Second eigenvalue is corresponding to second column of this S matrix, and each column of S matrix is nothing but individual eigenvectors. Okay, right? And the speciality about this particular bigger lambda matrix is this is diagonal matrix, you can see. Okay, so from this we can generate two different equations. So if you see, first let us do one thing. In both side, left and right hand side, multiplied by S inverse. Okay, and you will be getting A multiplied by S inverse equal to S multiplied by bigger lambda multiplied by S inverse. So in the left hand side, S and S inverse will become identity matrix. So identity matrix and A will become A. So we can write in that way A equal to S bigger lambda S inverse. Okay, this is one set of equation we are getting. Another equation can be, you just pre-multiply S inverse in both sides. Okay, so in that left hand side you will be getting S inverse AS equal to S inverse S bigger lambda. S inverse S in the right hand side will become identity matrix multiplied by bigger lambda will become bigger lambda only. So we can say that time S inverse AS equal to bigger lambda. So this is second set of equation. Both equations are very important. What this signifies, if you see the first one, that is nothing but a decomposition of a matrix into three different matrices. We are having our transformation matrix A, which we have decomposed into three different matrices. Okay, one is S, one is bigger lambda, one is S inverse. What is S, what is lambda, what is S inverse, all known. And the second equation has a special significance. If you see what we are doing, we are basically taking inverse of S matrix, we are multiplying with A, then we are multiplying with S. And if we do this kind of computation, we are converting the result into a diagonal matrix, because this bigger lambda, if you see bigger lambda is nothing but this one, right? This one we assumed as bigger, this particular symbol bigger lambda. The diagonal elements are basically eigen values. Okay, so along the diagonal there are basically eigen values present. So this particular equation is showing us that how we can convert any transformation matrix to a diagonal matrix. So we have to pre-multiply this S inverse, post-multiply S, and where in S, individual columns are basically the eigenvectors. Okay, and we will be getting the diagonal matrix where in each diagonal elements are basically eigenvalues. Okay, so this is nothing but called as diagonalization of transformation matrix, because by doing this kind of operation we are converting this A matrix to a diagonal matrix, right? This is having huge importance. Many application areas present in many domains, different domains. I'll be discussing about all of them in detail in my upcoming videos. So I hope you have enjoyed this particular session. If you find this video helpful, then please like, share and comment. Subscribe my channel if you have not subscribed till now. And don't forget to press the bell icon to get the notification of my latest videos. Thank you for watching.